All right, in this lecture, I want to talk about power, and, uh, and this goes along with energy. The first question kind of gets at why power is important. It says, why is it harder for the same person to run up a flight of stairs instead of walk if the change in PE gravity is the same? So in both cases, we can say that the work is the change in energy, which in both cases you're changing your potential energy gravitational the same amount, right? But in one you're doing it slower by walking, and one you're doing it quicker by running up the stairs. And so this gets at the idea of the difference being that of power. So by having a different amount of time that you accomplish the change in energy in, you have a different power value in both cases. So power is a couple ideas here. Let me see if I can. Power is the change in energy over time, right? And because power is also equal to, or change in energy is equal to work, we can say power equals work over time. We could also say if that's true, then power equals force times distance times the cosine of theta over time, right? Because that's what work is, ft cos theta. But we can also recognize something, and that's pointed out right here, is that we can recognize that d over t really is velocity. So we have another formula for power, right? And that would be that power equals fv cos theta. Okay, so a few different equations for power. But I guess the most important one to keep in mind, and you kind of can memorize the rest from this one, is that power equals the change in energy over time. And then just knowing that change in energy is work, you can kind of get the rest from that. But don't forget this one. I think this is one that students forget down here, that power equals force times velocity times the cosine of theta, because they always think of work as being ft cos theta, but just realizing that it can simplify into fv cosine theta for power. Okay, so power is the amount of the same type of energy converted to another type divided by time. If the process involves external forces, power is the amount of work. All right, done or on or by the system divided by time. Okay, power SI units here are joules per second, right? So we have joules divided by seconds, which we actually call something else. We call it watts. And watts is a capital W, which is confusing because work is a capital W. So we have two symbols that mean different things. Okay. Example 6.1 here. A person lifts a 13.6 kilogram barbell from the floor. Okay. Probably highlight that. To just below their waist. And they lifted a vertical distance of 0.7 meters. And time value of 0.8 seconds. Determine the power during the lift. Assume final initial positions don't include KE. We'll talk about that. Okay, so we have two ideas, I guess. If we write an energy balance for this, if we don't consider KE, right? So the bar starts on the ground, is then lifted up to some height. The energy type that it has at the end is going to be potential energy of gravity. But we also know that the lifting is going to do work on the bar, so or the person. So we'll say the work done by the lift. Now you might say, well, what about the work done by gravity? I think that gets at the idea. Well, this is the barbell, and here's the floor. When the person lifts the barbell up some height of 0.7 meters, this gets at the idea of what the system is, right? And we're saying, since there is potential energy gravity, that gravity is an internal force. So the Earth is in the system. I don't know if you can see my yellow dotted lines there. And so that's important there, right? So what we're saying is there is gravity does no work. So Earth I was gonna write in, let me just write is Earth is internal. So gravity does zero work. Now, if you assumed that there was kinetic energy, there was moving energy in the lift, then you would have to assume that the speed is constant. And KEI would equal KEF. So if you had KEI and KEF in there, they would both just cancel. So by assuming that there's no kinetic energy initial and no kinetic energy final, we accomplish the same thing. It's this, the formula simplifies into this, which is the work done lifting is equal to the potential energy U gravity final. What else can we say there? I guess that's about it, right? So let's think about that for a second. So if we're saying that that's true, then we're saying that the work lift divided by the time is equal to the power. And we're saying that the work lift up here is equal to mgh final, right? Which is equal to what there? I think we know the mass, 13.6 kilograms. I think we know all of this. I'm just going to go ahead and write it. Oh boy. I'm going to go ahead and write it down here. So we can say then the power is equal to mghf divided by T. Power is equal to 13.6 kilograms times 9.81 times, I think it was 0.7, yeah. And do we know the time? I think we do. 0.8 seconds. All right, and if we do the math there, I think I might already have it done. Yeah, I do. It's 116.739 joules per second, or we can say watts. All right. Okay. What else did I want to say there? What if we would have thought back here that, well, instead of thinking in terms of MGH, instead of thinking in terms of conservation of energy, you instead thought, well, you were just right here and were like, okay, the work lift is equal to the force lift times the distance lifted times the cosine of theta. And then you thought there for a second, you were like, okay, when you lift a barbell, that the force of the lift is going to be up, the distance is going to be up, and that's going to equal to 0.7 meters. So you were like, all right, force lift is the weight, so that's going to be mg, right? which is just the weight, right? Which is Fg. All right, Fg is mg. And then times 0.7 meters. What's theta here? If you go back up and look, the angle between both of these is 0. So theta equals 0 degrees. I'm running out of room here. I don't know if I can squeeze this in. I guess I'll try and write this way. Cosine is 0, which is just 1. So we can then say this becomes mg times 0.7 meters. My point is, this is the same, right? Divided by t, which for some reason I didn't write. This right here, let me see if I can get a highlighter. This right here is the same as this right here that we did over here. So either way is fine. If you didn't think of energy conservation and you were just like, isn't work just Ft cos theta? Yeah, it is. And that will get you to the same point. So I guess the important ideas here are to think about when work is being accomplished, what type of energy is changing. And here, the type of energy changing is definitely potential energy as this barbell is being lifted up into the air. All right, that's pretty much it. All right, divide that by the amount of time, and you got your power. Okay. A 1,400 kilogram car is traveling on a level road at a constant speed. I might draw this. In a constant speed, just say v, straight constant. I think we know what it is though. 27 meters per second. Okay. The drag force exerted by the air on the car and the rolling friction from the road add up to a net force of 680 newtons. All right, so there is a 680 Newton resistive force. Yeah, I'll put this in red. Just call it, yeah, we'll just call it drag. Could have called it resistive. I'm not sure what's the best there. I guess drag is technically just the air. I'll call it resistive. What the heck? F resist. All right, there we go. And then it says determine the rate of work done by, the rate of something is just something divided by time. All right, so work divided by time, rate of work, power. All right, that's code for power right there. Just make a point of noting that. Done by air and the road in watts and in horsepower. Oh, okay. And then they tell us a horsepower is equal to 646 watts. All right, so we want both here. All right, so what is the work done by the resistive force? Okay, so we can say then power is equal to work of the resistive force divided by time, which is equal to the force of the resistive force times, now here we don't know the distance, right? But we do know V. So this is our chance to use that other formula, right? And I don't need a fraction there because the time on the bottom, right? It's going to become this, because what I'm trying to say here is F resist times D times the cos theta divided by T. I'm saying that this right here is V. All right. So, okay. Let's go ahead then and keep solving here. So we can say then that power is equal to the force resistive, which is going to be 680, I think is what we said. Yeah. Times the velocity, which we know is 27 meters per second. There is a distance value that we don't know. Right? That's D there in blue. But we do know that because D points 180 degrees, right, opposite 180 degrees opposite of the force resistive, we know that theta is 180. So we can say cos 180 degrees, which is -1. And then we can go ahead and multiply here, and we can see that the power is equal to a magnitude of 18,360 watts. Or if we want to consider the fact that the work was done on the system to slow the object down, right? Negative work tends to slow an object down. We can consider it as negative 18,360 watts, and that's fine too. I forget which, if in the, I think in the textbook, they just want you to focus on the magnitude, so to not worry about the negative sign. So I'll just write or 18,360 watts. Okay. Good. I think that's about it. Yeah, that's all I got. So, good. Hopefully this is making sense, and I know some power questions will show up on the review guide, and take care.